All right, guys, so we're gonna jump right back into where we left off in the last video lesson. We learned that water can act as both an acid or a proton donor and as a base, a proton acceptor, okay? And what we call that is amphoteric, right, when it can act as both like that. All right, so I'm gonna breeze through the next few slides just because your other video lesson this week will cover some of these ideas. Okay, so we know that water dissociates into hydrogen ions and hydroxide ions. And remember, the hydrogen ion here is really a hydronium ion, but we represent it with hydrogen ions, okay? So in pure water, the concentration of those hydrogen ions is always going to be equal to the concentration of hydroxide ions, okay? So for pure water, the concentration of hydrogen ions is equal to 10 to the negative 7th moles per liter, and so is the concentration of hydroxide ions. This idea is going to be very important on the next few slides. Okay, so we're going to jump into this idea of an equilibrium constant, and this is in chapter 17 of your notes. So if you're looking through chapter 16 and you're like, I don't see anywhere about this equilibrium constant, go to chapter 17 and it's a small portion there. And what equilibrium is the exact balancing of two processes, right? One that is the opposite of the other. Okay, and what the equilibrium constant does is it expresses a ratio of product and reactant concentrations at equilibrium. Okay, and it's going to be some constant number, that ratio of products over reactants. Okay, so our equilibrium constant we represent with K. Okay, so K equals the concentration of products over the concentration of reactants for all systems that are at equilibrium. All right, so we're going to talk about this idea specifically with water. Okay, so again, we know that the concentration of hydrogen ions is always equal to the concentration of hydroxide ions in pure water, and that number is 10 to the negative 7. Okay, so the equilibrium constant of water equals the product of the concentration of hydrogen ions and concentration of hydroxide ions over the concentration of water. But since we're only dealing with water, that number can be crossed off because it is equal to 1. Okay, so really, the equilibrium constant of water is going to be equal to the product of hydrogen ions and hydroxide ions. Okay. So knowing that both of those numbers, the concentration of hydrogen ions and the concentration of hydroxide ions, is equal to 10 to the negative 7th, okay, we know that the equilibrium constant for water is going to be 10 to the negative 14th. Okay, and this is called the ion product constant for water. Okay, so here's a red box equation. Do be sure to write this one down. Okay, so K subscript W is the ion product constant for water, and it is equal to the product of hydrogen ions and hydroxide ions. Okay, give me 1 second. And because of this relationship, if the concentration of one goes up, the other must go down. Okay, so they have that inverse relationship, and this is true in any aqueous solution. Okay, so let's do an example to illustrate this. So if the concentration of hydrogen ions in some solution is equal to 10 to the negative 5th moles per liter, what is the concentration of hydroxide ions? And I like to use Jack's special little triangle. Okay, if you remember this guy, okay, if Kw, or the ion product constant for water, is equal to 10 to the negative 14th, okay, this number is going to equal the product of these bottom two sections, which is the concentration of hydrogen ions, apologies for the bad handwriting, and the concentration of hydroxide ions. Okay, so knowing that, if we're trying to solve for the concentration of hydroxide ions, I'm going to put 10 to the negative 14th over 10 to the negative 5th, which is my concentration of hydrogen ions. Okay, and that's going to yield 10 to the negative 9th for my concentration of hydroxide ions. All right, let's over here. Okay. Let's do one more example. Okay, so if I have the concentration of hydrogen ions equal to 3.65 times 10 to the negative third moles per liter in some solution, what is the concentration of my hydroxide ions? Okay, again, I'm just going to do 10 to the negative 14th over 3.65 times 10 to the negative third. And that's going to equal, if we do it on our calculators, 2.7 times 10 to the negative 12. Okay. All right. So there are a few more examples in the notes. Do take a look at those. But I'm going to skip forward to talking about pH. Okay. So pH is a measure of the concentration of hydrogen ions in solution. Okay. This is derived from a P scale, which is really just a scale that's based on the common log. So base 10 logs. All right, and it's always written as little p, big H. Do not write it in these other ways. Okay, those are incorrect. Right, so the pH is equal to the negative log of the concentration of hydrogen ions. Okay. All right, so let's move forward here. Hang on. Okay, so pH equals the negative log of the concentration of hydrogen ions. So therefore, the concentration of hydrogen ions is going to equal 10 to the negative pH. So in neutral water, we know that these two values, the concentration of both those ions, is equal to 10 to the negative 7. So the pH then is the negative log of 10 to the negative 7th, which is 7. And I'm sure you've seen that before. This is a neutral pH. Anything below 7 is going to be acidic. Anything above 7, therefore, is going to be basic. All right, so here we see the concentration of hydrogen ions on this side, okay? And if we take the negative log of these values on the left, we're going to get a pH of 1, 2, 3, 4, 5, 6, 7, all the way up to 14, okay? All right. I'm going to skip a few slides just for the sake of time, but here's an example. So what is the pH of a 12 molar solution of hydrogen chloride? Okay, so we know that hydrogen chloride dissociates into hydrogen and chlorine ions. Therefore, the concentration of hydrogen ions is going to equal 12. Okay, so what is the pH? Well, we plug it into our log and we take the negative log of 12 to get a pH of negative 1.1. Okay, let's do one more. Here are a few slides. I just want to point these out. These are the keystrokes that you would take on your calculator to do these equations. I'm going to skip them again for the sake of time, but do come back to these and practice on your own so that you're making sure to get the right values. All right, so we have pH, but we also have pOH, and basically pOH is going to mirror the behavior of pH because we know that there's an inverse relationship there. And pOH is just the level of, or the concentration of hydroxide ions. So pOH is going to therefore be the negative log of the concentration of hydroxide ions. Therefore, the concentration of hydroxide ions is equal to 10 to the negative pOH. Okay, this is exactly the same as with hydrogen. Okay, we remember that our ion product constant for water is going to be 10 to the negative 14. And if we plugged these values into our calculator, every time we would be getting that the negative log of the product, right, of the ion product constant for water is always going to be equal to the negative log of 10 to the negative 14. All right, so therefore, pH plus pOH is always going to equal 14. Okay, let's do some examples here. All right, so if I were given a solution with a pH of 4.2, okay, and I was asked to find the concentration of hydrogen and the concentration of hydroxide ions. Okay, so how we would do that is we would take this red box equation, pH plus POH equals 14, and I'm going to go here. Okay, so we know the pH is equal to 4.2. Okay, so 10 to the negative 4.2 is equal to 6.3 times, 6.3 times 10 to the negative 5, right? If I know that, I can determine the value. If I know that the pH is 4.2, I know the POH as well. And that's going to be 14 minus 4.2, which is 9.8. So 10 to the negative 9.8 is going to give me 1.6 times 10 to the negative 10. Okay, I apologize for my handwriting on this. I do not have a writing pad like Mr. Errett, so it's going to be a little more difficult. All right, let's do one more example. Actually, you know what? I'm going to skip ahead just for the sake of time. Okay, so neutralization reactions, we know that an acid and base will react to form water and some soluble salt. These salts are always ionic. Okay, if I were to write out the entire ionic equation, it would be NaOH for this reaction in particular of sodium hydroxide and hydrogen chloride. I'm going to get water and NaCl, or sodium chloride, which is table salt. Right? I would cross off my spectator ions in that sense. Okay, so we're going to use neutralization reactions in acid-base titrations. Okay, and what the point of these acid-base titrations is to determine the concentration of an unknown solution by reacting it with a known or standard concentration. Okay, so what we are going to do in these titrations is we're going to take precisely measured volumes of the standard and unknown, and we're going to determine the concentration of that unknown using those standards. Okay, we also need to use an indicator here. Okay, that standard solution is going to be a solution whose concentration has been accurately determined in the lab already. Okay, so for example, we had 1.039 molar sodium hydroxide in the lab. We could use that as a standard solution to determine the concentration of a different solution that we do not know. Okay. All right, so there are a few steps in titrations, and first we need to calculate the molarity of the unknown, and you'll recognize some of these steps. But as always, the first step is to write a balanced chemical equation for the reaction. Okay. Then you're going to use the volume of the standard known. Okay, so you know the concentration and you know the volume of your known standard. And you need to use that standard to neutralize the unknown. Okay. Then you're going to use a mole ratio from the chemical equation to convert moles of unknown neutralized. Okay. And finally, you're going to calculate the molarity of the unknown by dividing by the volume of the unknown. Okay. So we are going to do some examples of these to illustrate these steps, but I know some of you like to see all the steps outlined before the example. So here it is in words. Let's do it with numbers. We're going to do one example here. Okay, so what is the molarity of an unknown sulfuric acid solution if 10 milliliters of it is titrated to neutrality with 19.7 milliliters of 1.097 molar sodium hydroxide standard? Okay. All right, so the first thing I'm going to do here is I'm going to write my balanced chemical equation. So we have H2SO4 plus NaOH. It's going to yield water and sodium. All right. Okay, so this is not balanced. Let's throw in some coefficients. Okay, we need 2 of those and we need 2 of those. All right, so now I have a balanced chemical equation. So that is step 1. So now I'm going to use the volume of this standard known and calculate the moles needed to neutralize the unknown. Okay, so I see that I've got 19.7 milliliters. So there's my volume. And that's going to be converted to, if we're converting to liters, 0.0197 liters. Okay. My molarity is 1.097. Okay, so we've got 1.097 times 0.0197 liters. And that's going to give me 0.022 moles NaOH. Okay, so that is step 2 done. I've calculated the moles needed to neutralize the unknown. All right, so now I'm going to take those moles, 0.022 moles, and I'm going to multiply them by our coefficients, or our mole ratio, which we get from the coefficients of our balanced chemical equation. So I'm going to take that, I'm going to multiply it by, we have 1 H2SO4, and we've got 2 NaOH. All right, that's going to yield 0.0108, okay, and that's giving me my moles H2SO4. All right, so now I've got my moles H2SO4, but we're not done just yet. Let me extend the page here. It's not letting me. Okay, that's all right. All right, so I've got my moles H2SO4, and I know that that has to equal M times V, right? So I've got M. All right, so I know that moles, number of moles, whoops. M times V. Okay, so I've got 0.0108 moles equals my M, which we do not know, but we do know our volume, which is going to be 0.010 liters. Okay. All right, and we got that from up here, right? 10 milliliters is going to be equal to 0.01 liters. All right, so therefore I can calculate my molarity. So that's going to be equal to 1.08 moles per liter. And that's going to be of H2SO4. All right, so that is one example. There's another way to do this normality, which we will get to next time for the sake of time. All right.